Hey guys, Mr. Ray here. Um, we are going to continue on with our application of derivatives, and I actually have some good news for you. Uh, I thought there was two more lessons, but the second lesson was actually one we've already done. That was the velocity and acceleration lesson that I kind of moved up the order a bit, just to stay on the same timeline as the other teachers. So um, that lesson and the associated homework with it, along with the previous lesson and today's lesson, that's basically the unit. This will be the tough lesson. Not so much in the technique. Just we have several examples. I want to go through quite a few problems. I was thinking about breaking it up into two lessons, uh, but if you get if you get bored of my voice, which I'm sure is very possible, or it's just too much at once, just pause it, come back to it the next day. This is the last lesson of the course. Um, Now for the assignment, I'm still going to go ahead and wait until next week. So um, I'm thinking maybe release the lesson on Google Classroom. I'll do the same time, like 3 p.m. on Monday. Have a 5% bonus if you get it in by, I forget what it was, 9 o'clock, 8 o'clock, whatever the usual time is. But it will be due on the actual due date will be the following Sunday, like normal. So you'll have lots of time to work on it. I also need everyone to finish up the lessons, or sorry, the assignments. I still have a group of between 5 and 8 people that are behind. Once I start marking a lesson and returning it, that's basically it. If you haven't uh, submitted your assignment by then, it's a zero. So that's your warning. If I have some people that haven't done assignment 3. Sometimes people are skipping them. So, anyways, get those assignments in. I will have another couple marked and returned this week, like I said in the note on Google Classroom yesterday. Um, One other thing, before now we did skip a fair amount of content in the course to try to just prioritize. So we basically skipped all the derivatives of um, log, log and not log, exponential and uh, trigonometric functions. So what I'm going to do, I'll probably wait till the weekend, send out a little survey, and basically I'm going to ask, um, are you guys interested in learning about that? Now, what I what I what I'm kind of proposing to do is I'm just going to release the notes, the basically the filled in lessons for the those two units, and you can go through them. You can kind of figure out what is the derivative of sine. Um, you know, some of the more complicated ones. Um, I won't be doing any testing on that, even if you want to learn it. But I know there's again a handful of you that are going to be taking this in university next year. Um, so if you're interested, I will put those lessons out as just as um, an interest thing. Okay, so all right, so let's get back to the lesson. Um, so what we're going to do, if you remember last time, we did maximum minimums over an interval. So something like if you had maybe you had some kind of function like this, and you wanted to, obviously the function keeps going in all the directions, and you wanted to find the local min or the extreme um, global min and max values between, say, so there's your x-axis. Say we wanted to know between that value of x and that value of x. So what we learned last time, first thing we do is we do the first derivative. We find the critical points, test the actual value. So that would give us these two values. And at the same time, we test the border points, basically on the interval, edge of the interval. We find those values, and then if you're asked what's the global max for this interval, you would test all four, and it looks like that would be the global max, and this would be the global min. Okay, so we're going to continue that with our lesson today on optimization problems. And you're going to see, like I kind of foreshadowed last time, we're going to do, I think, 3 problems you might have done in grade 10, but we're going to use it, we're going to find the optimal values using derivatives. Okay, so all right, so in an optimization problem, which this is all about, you must determine the minimum or maximum value of the quantity, and it will tell you in the question. Sometimes they actually ask for both, but usually it's just one or the other. An optimization problem can be solved using a mathematical model that is developed using information given in the problem. So if you're trying to do things like optimize volume, obviously your starting equation will be a volume equation, or if it's an area optimization, or if it's a revenue optimization. Okay, you'll create that equation, and then we'll work from there. Okay, so we've got prof, cost, and revenue or quantities whose rates of change are measured in terms of the number of units produced or sold. To maximize revenue, this is straight from grade 10. We can use the revenue function. Revenue equals total revenue from the sale of X units, which is the price times the number sold. Now, what we're adding in here is this. So this is important. We have to consider practical constraints as well as mathematical constraints. And we'll get to these once we're there. But we have to consider other things than the mathematics and put constraints as they relate to the variables we use. And that will determine our basically our interval that we're looking for and testing for. Okay, once the constraints in the model have been determined, as in what's the domain of this situation, apply the extreme value algorithm. So this is basically what we did in lesson 1, the previous lesson, over appropriately defined domain to determine the absolute extreme. And that was using what I was talking about up here. Okay, so let's forget how many questions we have here. I think it's 5. Oh, just 4. Oh, maybe it's 5. It is 5. Okay, so let's start off with one that you'll recognize from grade 10. Okay, a farmer has 800 meters of fencing and wishes to enclose a rectangular field. On one side of the field is against a country road that's already fenced, so the farmer needs to fence only the remaining 3 sides of the field. The farmer wants to enclose the maximum possible area and use all the fencing. How does the farmer determine the dimensions to achieve this goal? Okay, so obviously you may remember this from grade 10, but there's the fence on the road, and you're going to build a rectangle. And you probably remember from grade 9 and 10 when we did this, that this should work out that this side is half the length of this side. Usually that's the way, but let's assume we don't know that. Okay, so that's the fence there. We'll introduce our variables, so x will be basically those lengths there. Now we have 800 meters of fence. We've used x here, x meters here, x meters here. A total of 2x meters have been used. So what do we have left? We have 800 minus 2x. So that will be used on the third side. Okay, remember we don't have to fence that side. There's already a fence there. So we're trying to maximize area, so that means we should have an area function. So the area based on x is just the length times the width, which is x times 800 minus 2x. If we expand this, you're going to get negative 2x squared plus 800x. So there's the area function. So just like we did in the first lesson, we're now going to take the derivative. So a prime of x, so the derivative of the area function, that's going to be negative 4x plus 800. And now to find the critical points, we set it to 0. and you'll see pretty quickly that for x equals 800, so x equals 200. That's basically, because that's the first derivative, that's a critical point. So it could be a max, could be a min, could be neither, but it's the only critical point. Now the other thing we have to consider is the constraints on the variable. Okay, so what does that mean? Well, if we go back to this diagram of the model, one of the constraints is the length and the width have to be greater than 0. Okay, so from this variable here, we know that x is greater than I guess it could be 0, but you'll see that it doesn't really matter. X is greater than or equal to 0, and then from this one, you know that 800 minus 2x has to be greater than or equal to 0, because that's the other dimension. And if we solve for this basically, if we add 2x to both sides, we'll see that x has to be less than or equal to 400. And you could probably see that already, that for this to be 0 or positive, x has to be less than or equal to 400. Okay, so if we put these two constraints together into one constraint, we see that x is going to be between 0 and 400. Okay, so that basically defines the valid interval for our variable x. So we're going to test the critical point that we found, x equals 200, and the two interval endpoints based on the variable constraint. So we're actually testing for, now we're going to plug these values back into the area equation. So a of 0, a of 200, and a of 400. Okay, now when you do this, plug in 0 here, we're actually going to get no area, because that makes that one dimension 0. And we get the same thing for 400, because if 400 is plugged in, this side becomes 0. Okay, so you're almost thinking, well, why bother? Why did we even bother with these points? Well, in this example, it didn't really matter, but in many examples, you may find that one of these interval endpoints is the local min, or the global min or max for that interval. So we still have to go through the routine of checking them. Okay, and then a of 200, if we plug that in, we get 80,000, and the units would be meters squared for all three of them. Okay, so we now go back, we want the maximum possible area, obviously, so that's going to be this value here. Okay, so therefore the maximum area of 80,000 meters squared is created by a 200 by, so now we take the 200, we can plug it back into here to get the dimensions. So that would be 200, that would be 800 minus 400, so that's 400. 200 by 400 meter rectangle. Okay, so very similar question to what you would have had in grade 10. And if you think about it, how did we solve this in grade 10? We found the vertex. And the vertex in a quadratic is a critical point. It's well, it's either a local min or local max. So we're just finding it, not calling it a vertex, but calling it a critical point, and then testing the necessary endpoints as well. Okay, so that's how we do it in calculus. Okay, the next one's also something you might remember from grade 10. You have a piece of sheet metal, 60 centimeters by 30 centimeters. Okay, it's used to make a rectangular box with an open top. Determine the dimensions that will give the box the largest volume. So if you remember this one, you draw this. This kind of helps you figure out how to do it. But you cut out these x by x corners in each of the 4 corners, and that allows you to, where the dotted lines are, you fold up the edge on all 4 sides and you create a box. So we're trying to create the box with the largest volume. Okay, so obviously volume is the equation that we're going to start with. So v of x. So we look at the 3 dimensions, length, width, and height. Well, the easy one is x, because that's going to be the height when you fold it up. So we've got x times, and then so the width here, we started with 60, but we took away x centimeters here, x centimeters here. So that would be 60 minus 2x. It's kind of like that, if you remember those cutting the grass question with the border, or maybe even a picture frame. We had those in grade 10 as well. So, and then the other dimension would be this. It started at 30, take away x, take away another x. So that's 30 minus 2x. Now, you actually could take the derivative of that using the product rule a couple times, but I personally would expand this out. And when you do that, I'll just skip to the fully simplified version. 4x cubed minus 180x squared plus 1800x. That's the volume. And now we're going to take the derivative, v prime of x. It's a lot easier to take derivatives when it's just a polynomial. So 12x squared minus 360x plus 1800. And to find the critical points, set it to 0. Now you can factor, just to make it a little easier, you can notice that we can actually factor out a 12 from both. And factoring out a constant, it's not going to change, because if I factor out the 12 and then divide both sides by 12, I still get 0 here, and I get the factored version without the 12. So that's a perfectly legitimate way of doing it. So if I factor out the 12, I get x squared minus 30x plus 150. Now, you think that might be factorable, but it's not. If you plug this into quadratic formula, I'll just put how we got it, quadratic formula, we get x is equal to 30 plus or minus, I believe that's 300, over 2. So when you do both branches of that, you get 23.7 or 6.3. Okay, now we got to concern ourselves with the restrictions on the domain. So that's, what values of x can we use? What are the, the domain? So again, we look at the 3 dimensions here. So, if I looked at these separately again, height is x, length is 60 minus 2x, width is 30 minus 2x. Okay, so if I look at the restriction on here, for the height, that just means x has to be greater than equal to 0. Here has to be less than or equal to 30, so that the length is not negative. And here this would be 15. So x has to be less than or equal to 15. Now these all have to be honored. You can't just pick. So this is kind of the bottom limit. X has to be at least 0. Now if you put these two together, it might be a little confusing. This one says it has to be less than 30. This one says it has to be less than or equal to 15. We have to honor the one that helps both of them. So this is the most restrictive one. If I plug a 15 in here, I'll get a 0. If I plug a 15 in here, I'll get 30. Okay, so you're basically looking at combining these two restrictions on the domain. So the new domain is between 0, x is between 0 and 15. Okay, so now I didn't really talk about these values because I wanted to wait till we looked at the domain and what restrictions we had. This says x has to be between 0 and 15. That one's fine. This one's not. So that one we rule out right away. Even though it's a critical point, it doesn't honor the domain restrictions. So it's basically eliminated right away. So what we do is we're going to look at the values 0, 15, and 6.3. Okay, so I plug those into the volume. So volume of 0, volume of 6.3, volume of 15. Okay, hopefully everyone sees where that comes from, the two endpoints plus any critical values that are still within that. When I plug these in, I get 0 cubic centimeters. So is this one, because it makes the one, it makes this side 0. Okay, but if I use 6.3, I get 5196 centimeters cubed. And this one's pretty obvious, just like the last one. What's the highest, what's the largest volume out of these three? Obviously, it's that one. So, x being 6.3 gives us the largest possible volume. So if I plug those back into the three, well, I guess I could look at these, into these three dimensions. So, therefore, our box, 6.3 would be the height. If I plug 6.3 into the other ones, if I plug it into here, it works out to 47.4 by, and if I plug in 6.3 here, I get 17.4. So all three of these dimensions of the box are in centimeters, and that will give, and you can say maximum, because we know that now, a max volume of 5196 centimeters, and it's cubed because it's volume. Okay, so similarities to what we did in grade 10, but a little wrinkle with the derivative and looking at the domain, checking those values as well for the volume. So far we haven't had to use those, but you never know. You still have to do it to make to get full marks. Okay. All right, this one is totally different. This one is something you never saw in grade 10. And when you first look at it, it looks pretty complicated. So just bear with me here. So Ian and Ada are both training for a marathon. Ian's house is located 20 kilometers north of Ada's. So maybe I'll just start a little picture. So there's Ada's house, and there's Ian's house. It's directly north. Okay, so that's 20 kilometers total. At 9 a.m. one Saturday, Ian leaves the house and jogs south at 8 kilometers per hour. So he's headed south towards Ada's house at 8 kilometers per hour. And at the same time that Ian leaves, Ada also leaves her house. She's jogging at 6 kilometers per hour, and she's jogging east. So she's going this way. So Ian is traveling that way. Sorry, that's not a very good arrow. Ian's going this way, Ada's going this way. So maybe Ada doesn't really like Ian. Not sure situation here. When are Ian and Ada closest together, given that they both run for 2.5 hours? So basically, they run for Ian goes for 2.5 hours that way, 2.5 hour, Ada goes that way, at their different speeds. And there'll be a point that they both, so Ada will end up here, we'll call this B. And Ian will get to this point, we'll call it J. After 2.5 hours, after 2.5 hours, this might not be to scale. So that line there is the distance they're apart. Okay, and let's call this S. So let's do a bit more work here. We haven't really incorporated the actual distances and the speeds. Okay, um, so let's start with Ada. It's a little simpler for her. Ada is traveling for 2.5 hours, and she's traveling at well, let me just think about this. Okay. All right. So we're not going to bring in the actual time that they ran for, but that will be part of the constraint. Okay. So let's just say we don't know how long they ran for at this point. But if Ian jogs 8 kilometers per hour, and we're going to use the variable t. Maybe we'll introduce our variable here. So we can do that here. Ian starts at I. That's the point I. Reaches j after t hours. So there's our variable. Okay. Ada starts at A, and she reaches B after t hours also. So both t hours. Okay. So if Ada travels for t hours, she's traveling at 6 kilometers per hour. So the distance she travels here will be 6 times the number of hours. So that will be 6t. Ian travels 8 kilometers per hour for t hours. So going from I to j, that will be 8t. Okay, because that's where he started, that's where he ended. Ada was over here. So obviously this is not to scale, but it doesn't necessarily have to be as long as all the information is accurate. Okay, so what about this side? Because you can kind of see, hopefully some of you will say, oh, we're building a right triangle here, and we're going to possibly try to use maybe Pythagorean theorem to maximize, or in this case, minimize s. Okay, so what's this side here? Well, we know the entire distance from I to A is 20 kilometers. We know we traveled 8t kilometers. So this side here is 20 minus 8t. Okay, so now we've got our 3 sides of the triangle. Okay, now you could start this off a little simpler at this point for the formula. You could say that s squared is equal to 20 minus 8t squared plus 6t squared. I'm going to rearrange it already. So if I'm trying to solve for s based on time, s of t, that's going to be equal to the square root of these two sides combined. The squaring of both of those sides added together. So I've got 20 minus 8t squared plus 6t squared. Important to have the brackets. Obviously you have to have the brackets there, but you also have to have it there because you're squaring the 6 also. Okay, now if you expand this out, keep it all under the square root, we're going to get 100 t squared minus 320 t plus 400. Okay, so that's as simplified as we can get. I'm going to take the derivative of this, so because I want to find the critical points, which will give me possible optimal values. Now I'm not going to show all the steps here, but if you're taking the derivative of this, you put brackets to the power 1/2, and that's like a composite function. Hopefully you remember from a couple units ago how to do this. I believe the solution is in the textbook. Not 100% sure, but you could try it out yourself. Make sure you get it. When we take the derivative, we get 1/2 100t squared minus 320t. Yeah, so we'll do a couple steps here just to show you what we're doing. Plus 400. Remember, we reduce the power by 1, so that becomes -1/2. And then 200t minus, this is the derivative of the inside function, minus 320. Okay, and I'll do two things. I'll simplify this a bit. I'll also set this to 0 at the same time. This becomes, so this is the part that stays on the top, 200t minus 320. Hold on, that's not it. It's half of that. We'll incorporate the yeah, so one half times that becomes 100t minus 160. And then on the bottom, you've got your square root. If we move this to the bottom, turn it positive, square root 100t squared minus 320t plus 400. All right, now the good news is we don't even really need this denominator part. If we're trying to set this to 0, it just means that 0 is equal to 100t minus 160. And if we solve for that, we get t equals 1.6. Only one critical point. And in all likelihood, that's probably going to be, remember this stands for the time they ran. Okay, that's probably going to the time that gives the closest distance, but we still have to look at restrictions on the variable t, the domain of t. Okay, so for the 6t, so if I'm looking at the two sides, well, let's look at all three sides. So ij is one side, ja is another side. That's this, and this. We have to make sure those values are greater than 0 at least. AV equals 6. So that's 6t. This is 8t, and this is 20 minus 8t. Okay, so what do we have to do to make sure all three of these are positive? Well, it has to be at least 0 for these two guys. So for these two, t is greater than or equal to 0. For this one, t has to be less than or equal to 2.5. Because if t is 2.5, this becomes ja is 0. Okay, so this tells us overall that t has to be between 0 and 2.5 to make all these three distances non-negative. Okay, so these become our endpoints. So just like before, we plug these two values plus the 1.6 back into our distance equation. So we have s at 0, s at 1.6, and s at 2.5. And we plug these back into the original distance equation. S of t, we get, this time it's not zeros, which is nice. This distance would be 20 kilometers. So basically, you kind of know that if they don't run at all, and they're just at their houses, that would be 20 kilometers apart. So that one's probably not going to be the value. If I plug 1.6 in, I get 12 kilometers. So we're looking for the lowest value, so far that's the best. And if I do it for 2.5, I get 15 kilometers. So the minimal, closest distance happens after 1.6 hours, and they're going to be 12 kilometers apart. Okay, and you can see this time, it actually was, closer than the last two cases. So you can see the requirement to have to check these, because it will definitely be cases where you will take one of the interval extreme values. Okay, so therefore the minimum distance between them is 12 kilometers, which we got from there. Now, here's where you can show off your math skills. Now, I just said it doesn't make a lot of sense, because the question says when are they closest together, being that they run for, well, the 2.5 hours was the maximum anyways. Because I guess after 2.5 hours, Ian would get to Ada's house and stop. So you notice they actually told us what time they left. They both left at 9 a.m. So we should be saying what time are they 12 kilometers apart. So this is where you do your math. 1.6 hours. Don't forget an hour is 60 minutes. So that's 60 minutes, and that's 36 minutes. So 96 minutes apart. So 96 minutes after 9 o'clock would be 10:36 a.m. So that's pretty accurate. Okay. So this is kind of a cool question. But you can see you have to develop some kind of, a diagram that will give you some of the values, some of the expressions. And we're actually trying to minimize this distance. So we have to come up with an equation involving solving for S based on T. Okay. So that was probably the hard part here, but that's kind of an interesting problem. All right. Probably the most famous quadratic word problems many people had issues with were the maximum revenue questions. Okay, so this looks exactly like the other ones, except there's a couple of restrictions. Commuter train carries 2,000 passengers daily from suburb into a large city. The cost to ride the train is $7 per person. Market research shows that 40 fewer people would ride the train for each 10-cent increase in the fare, and 40 more people would ride the train for each 10-cent decrease. So they've actually showed both directions, which we didn't do in grade 10, but it was actually true then. Didn't want to confuse all those young minds though. Okay, now here's the new part. If the capacity of the train is 2,600 passengers and carrying fewer than 1,600 passengers means costs exceed revenue. So, if you're taking less than 1,600 passengers, you're losing money. You don't want that. And 2,600 is the maximum. That's a physical limitation on the train. So these are restrictions that we're going to include. So just like we did in grade 10, let X represent the number of increases. Now you could go either way with this, whether it's an increase or decrease. Your equation will change with the signs. So this will be 10-cent increases. Okay, so again, revenue based on X, the number of increases. So remember, the fare starts off at $7. In this case, we're increasing it by 10 cents, so that's plus 0.1x. And at $7, it was carrying 2,000 passengers, 2,000, and we're going to lose 40 people for each increase. Okay, so that should seem familiar. Now, usually when I would do these questions, I'd just say find the zeros and then find the vertex from the midpoint between these two zeros. But we can't, we're going to use calculus. So I'm going to, it's much easier to take a derivative from a polynomial function. So you could do this with, the product rule if you're adventurous. But if we expand, simplify, we get r of x is equal to negative 4x squared minus 80x plus 14,000. And if we take the derivative, okay, not too hard, negative 8x minus 80, set that to 0, and well, I guess I have to write this again. So we get 8x equals negative 80, x is equal to negative 10. Okay, so that's the one and only critical point. That's most likely where the vertex is, but we're doing it a different way. So what I want to do now is talk about these restrictions. So we can't have any more than 2,600 passengers, and we can't have any fewer than 1,600. Okay, so how does that affect X? Because this is passengers. This is not the value of X. So we have to relate, what's the restriction on X for that number of passengers? What's the restriction on X for that number of passengers? Okay, so we get that from here. Okay, the 2,000 minus 40X, that's the number of tickets sold, which is the same as the number of passengers. So our first condition, 2,000 minus 40X, has to be less than 2,600. That's the capacity of the train. If I subtract 2,000 from both sides. Now, remember this with inequalities. If you divide by negative or multiply by negative, you have to flip the direction of the inequality. So if you divide by negative 40, it changes to X is greater than or equal to negative 15. So that's the condition, so that we don't have any more than 2,600 passengers. And then the second condition, it starts off the same way. This is the number of passengers. That has to be greater than 1,600 this time. So that's a 2,000. Subtract 2,000 from both sides. We get negative 40X greater than or equal to negative 400. Now this time, again, dividing by negative 40, sign flips. So that becomes 10. So here, X has to be less than or equal to 10, has to be greater than or equal to 15. Put them together. X has to be between 10 and negative 15. Okay, so what values do we test? Well, we test the critical point we found. We also test the two endpoints of the domain. So plug them in. R at negative 15, R at negative 10, and R at positive 10. Okay, so here we get 14,300 when we plug it in. That's the revenue. And here we get 14,400. Here we get 12,800. Okay, so again, we're looking for a maximum revenue, largest possible. That is this value here, which happens when we have negative 10 price increases, which is the same as 10 price decreases. So it probably sounds better when you say 10 price decreases than negative 10 price increases. So let's do that. Let's flip it around. Therefore, max revenue occurs when there are 10 price decreases. But that's not X equals 10, that's X equals negative 10. If we plug that in, therefore the fare, the price of the ticket, so if X is negative 10, it gets, that would be minus $1. That would be a new fare that's $6 per ticket. And the number of passengers, well, we definitely know it's between 1,600 and 2,600. If we plug in the negative 10 here, it actually adds 400, so 2,400. And the revenue, if we multiply these two together, is 14,400, which we already did when we plugged in X equals negative 10 there. But this summarizes the situation that we want to have to maximize revenue. Okay. All right, very last question of the course. This one's a doozy. So if you're feeling a little bit sleepy at this point, you might want to come back to this question with an alert mind. This has to do with the volume of a cylinder and some different questions. This is a tough question for sure. Okay. A cylindrical chemical storage tank with a capacity of 1,000 cubic meters is going to be constructed in a warehouse that is 12 meters by 15 meters with a height of 11 meters. So this tank has to fit inside the warehouse. That's where this is coming from. The specifications call for a base to be made of sheet metal, or sheet steel, that costs $100 per square meter. The top to be made of steel that costs $50 per square meter, and the wall to be made of sheet steel that costs $80 per meter squared. So you can kind of see this is a tough question. So the first part is just see if this is possible based on the restriction of the warehouse, and that you have to be able to store this, have this tank. Okay, so determine whether it's possible for a tank of this capacity to fit in the warehouse. If it is possible, state the restriction on the radius. So this is the radius of the cylindrical tank. Okay. All right. So the big formula we're going to use, volume of a cylinder is V equals pi r squared h. Okay. So draw a little picture. Here's my cylindrical tank. The radius goes from here to here. The height goes here. Okay, now the floor plan, if you remember, it was, the floor was 12 by 15, 12 meters, 15 meters, and we have a cylinder, the cylinder has to fit in here. This is the floor. Okay, so that's going to restrict the radius of the tank. So the restriction here is on the 12 meters, obviously, the 15 won't be the issue. So that means that if I maxed out on that 12 meters, the radius has to be less than 6 meters. Actually less than or equal to. And if you think about it, so I'll put that over here, radius is less than or equal to 6 meters, and that's from this, the floor. Now the ceiling is 11 meters high, so that puts a restriction on the height of the cylinder. It has to be less than or equal to 11 meters. Now, you notice these are two different variables, okay? So I can't put a restriction on, well, the actual equation will be based on one of these variables. So what we're going to do is we're going to convert the height into an expression or value for the radius. So if the height is equal to 11 meters, here's where we do our, so take this from the volume, pi r squared h, so we know h is 11, it has to be 1,000 cubic meters, right? So we're just basically solving for r. So if I basically divide by 11 pi, I get r squared is 1,000 over 11 pi. And if I solve this, I get r is equal to 5.38 meters. Okay, so that converts the height restriction into a radius restriction. So if I combine these two together, I know that r has to be less than or equal to 6, but also has to be greater than or equal to 5.38. So somewhere in between, there's the restriction, and it is possible. Yes, it's possible. And there's the restriction. Okay, so we know we can go forward. The second part, I don't think they'd ask this question if it wasn't possible. If it is possible, determine the proportions, basically the dimensions that meet the conditions and minimize the cost of the steel for construction. Okay, so never had anything close to this in grade 10. This is where the power of grade 12 and calculus comes through. So let's get some expressions for the cost. Remember, if we go back here, there was 3 different steels being used and different costs for each type. So I'm going to break this down into the 3 things: the base, the top, and the wall. And so this is going to be the cost. So the base, where's the base? It's $100 per meter, per square meter. So if we figure out, so the base is a circle. It's this part right here. So that's pi r squared. We're going to need that. So it's pi r squared times the cost for a square meter. So that's 100 pi r squared. Okay, the top, again, it's the same pi r squared, but this time it's $50 instead of $100 per square meter, so that's 50 pi r squared. Okay, and then the wall is the trickier one. Okay, so the wall is $80 per square meter. So if you remember the wall, if you cut this, it's basically a big rectangle. The top part is 2 pi r, and then the height is h. So it's 2 pi r h square meters for the wall times $80 per square meter. Now again, we've got the 2 variables here. So I want to convert everything into r. So I need to change the h. So so that's 2 pi r, and then the h is going to be 1,000 over pi r squared. Okay, so the way we get the value for h is we can just go back to the original volume. We know the volume is 1,000. So if I just isolate for h, divide both sides by pi r squared, I get 1,000 over pi r squared. So that's where that comes from. Now I've got all 3 of these costs based on the radius. Okay, I don't have to worry about that h anymore. Now I can simplify this a bit. I can cancel out the pi's. I can cancel out one of the r's. And when I do that, it works out to 160,000 over r. Okay? So what I'm going to do now is have a cost function with the radius as the input. So it's basically combining all 3 of these together. So these 2 we can easily combine. That's 150 pi r squared. Okay, and then we just add on this cost, 160,000 over r. There's our formula for the cost. Now we want to find the critical points of that, max and mins, and to be able to test them out. So take the derivative of that. Okay, and remember it's the r that we're using as our variable. So that's going to be 2 times 150 times pi, that's not a variable, it's a constant. And then this one here becomes minus 160,000 over, sorry, it's a minus, yeah, I got that, over r squared. Because you would just treat this as 160,000 r to the -1, okay, and that would be the derivative of that term. Okay, so there's our derivative, so set this to 0. Okay, we can actually move this to the other side here. 160,000 over r squared is equal to 300 pi r. Okay, we'll multiply both sides by r squared. 300 pi r cubed. Now we divide both sides by, so basically it becomes r cubed is equal to 160,000 over 300 pi, and then we just take the cube root of that value, so I'll just go right to the answer. R is equal to 5.54, and of course that's in meters. All right, there's our one and only critical value. Now we've already got our restrictions on R from the first part of the question. We know R has to be between 5.38 and 6, and while we're at it, we can check this value, make sure it's in that domain, and it is. So we're going to do our three costs based on the value of R. So first one is 5.38, second one is this value here, and the third one is the upper value of the domain, C of 6. Plug those guys in, we get, for this one, cost is 43,380. This one is 43,344, and this one is 43,631. And you can see it's pretty close, but this one, which was our critical value, is our minimum cost. So therefore, minimal cost is $43,344 when the radius, so the radius of 5.54 meters, and the height. Now, to get the height, where was that value here? Yeah, so to get the height, we'd use this expression here. We'd plug in our R value of 5.54, so it's 1,000 divided by 1,000 divided by pi times 5.54 squared, and that gives us a value of 10.37 meters. And you can see with these dimensions, it's not too tall for the building, and the 5.54 is less than the 6. So this will fit in the building, and it is the minimum cost. So that's quite a doozy question. You will be getting assignments. It's got several word problems related to what we've been doing today, plus some more general questions from lessons 1 that we just finished last time, and the velocity acceleration. Okay, so that assignment, like I said, that'll be released. I'll send you guys a notice to remind you, but I'm probably going to release it at 3 p.m. on Monday with a bonus for later that night, and it will be due on Sunday. Okay? All right, so I will, like I said, I'll put a vote out, see if anyone's interested. As long as one person's interested, I will put those notes on Google Classroom. You can do with what you want. You could ignore it, you can print them off, you can look through them, up to you. I don't want to take the time in putting them up if no one's interested though, okay? So that'll be it, that's it for the course. I will be sending out several marked assignments this week. I should be caught up. I should get all the existing assignments done by the time this next assignment is due, and then I'll be able to mark that one fairly quickly. Okay, so have a good week, guys, and I'll send you out more information. Thanks.